So sometimes the hypotheses we'll want to test are about a proportion. When that's the case, we will use a z-test. So a z-test for a proportion. And remember, for us, proportion can be a proportion or, right, a percent. We mean the same thing. So we need some assumptions for testing a proportion. So first off, the sample is random. And then this one, that n times p is greater than or equal to 5, and n times q is greater than or equal to 5. Now for both of these, the p and the q are from your hypotheses. So not from what your sample tells you, but from your hypotheses. But n, right, is the sample size, just like it always is. Okay. So, right, in most book problems, we're not really going to have to worry about this too much. So how is this hypothesis test different from the others? Well, the formula for calculating the test value is different. Well, okay, it's different, but it's the same. So here's how it's the same. So the test value is observed minus expected divided by the standard error. That's how it's the same. How it's different is how we would get the standard error. Okay. So one more thing. Observed, so this is from your sample. Expected, this is from the null hypothesis. And the standard error is p square root of pq over n. But, so even though this is, right, we can write our formula. So here we go, test value equals observed. So this is the proportion of our sample, so that's a p hat. Minus expected, that's from our null hypothesis, so a p. Divided by the standard error, so p from the hypotheses, q is 1 minus p, divided by n. So I have this division for my big fraction, and then I have a division in the denominator itself. Okay, so this will tell us the test value. But we can also use your calculator, which is what I'm going to do. One more thing before I go, and that is the p hat. So from our sample, sometimes they'll just tell us, sometimes we'll be given the percentage or the proportion for our sample, but sometimes they'll tell us the x value, how many had it, and we'll need to divide that by the total number in the sample size. Okay, so here we go. So that's how the formula is different. Otherwise different, we'll use the z distribution, like with means when you know sigma. And our hypotheses have p's and not mu's. Okay, so I'm really going to be on the lookout for that. If you're doing a hypothesis test on proportions, I'm going to expect to see p's here, and I'm not going to be really happy if I see mu's. Okay, so here we go. Example 1. The percentage of female physicians in 2010 was found to be 32.4% by this website. At Central Washington Hospital, I did a very unscientific study and found that out of a sample of 20 physicians, 6 are female. Adelphos 0.01 is the percent of female physicians in Wenatchee different than the national value. Okay, so we're going to go through those same steps of hypothesis testing. We're going to write our hypotheses. So P equals, the null hypothesis gets the equal sign, 32.4%. Now for our alternative, we have to decide what sort of inequality symbol we want. Let's see, different, right? So different says not equal to, and we'll make that the claim since we don't have something specific for the other one. So gather the data. This is the info session. So I'm going to stick it up here just so I have a little bit more room. Okay, so for the info, what do we know? In a sample of 20, right, so 20 was the sample size, so that'll be n. 6 are female, so that's the number that had the characteristic of being female. And now we know that alpha is 0.01. Okay, is the percentage different? All right, so there's our data. So what is p hat? Right? So p hat is 6 over 20. And if you want to do that on your calculator, you'll see that that's 0.3 if you write it as a decimal, or 30%. Okay, now the critical values. So for proportions, our critical values come from the Z distribution. Sorry, I phased out there. I was just checking to make sure that our n times p and n times q are going to be 5 or bigger. So 0.3 times 20 gets us to 6. So that's bigger than 5. So we're good to go. Okay, so back here, critical values are from our Z distribution. We have a two-tailed test, and alpha is 0.01. So you can either use your T distribution and go to the bottom, right? Go across on the two-tailed test and go all the way to the bottom. Maybe you just know these by now because you've done so many of them. So I actually didn't have either of those options to me. So I had to grab my calculator and remember how to find the area under the curve. So I have 0.01, it's a two-tailed test. So 0.01, so that's 1%. So I need 99% in the middle. That means I have 1% to share, so that's 0.5% on either tail. So I need the values that cut off, right, the outer 0.5%. And my calculator, if I do the inverse normal, which lives in the distribution menu, and I give it the area of 0.005, so I'm taking the 0.5 and turning it into a decimal, then it will tell me that that left side is negative 2.576. And my right side would be positive 2.576. So those are my critical values. And so the rejection region is in the tails, 0 in the middle. So now we have to come up with a test value. So back on the calculator. So now it's the stat option. So stat and then over to tests. And we want to do, so we're doing proportions. And this is one sample. So you're looking, so even though it is a z-test, this first option that you see is a z-test for means. If you accidentally click that one, you're going to know you're in trouble because the calculator will ask you for a mu value, and you don't have any mu's, all you have are p's. So we need to look down until we find one sample, one proportion z-test. There we go. It looks like it's option 5. So option 5, and it asks for p naught. P naught comes from our null hypothesis, so make it a decimal. Go ahead and type that in. X, this X value is the amount from our sample. So what was the X from our sample? Ours was 6. And N was 20. And then finally, again, we tell it what is our alternative hypothesis, and mine is a not equal, so I'll go ahead and select that and then calculate. And it's kind of nice because the very first line, it reminds you of your alternative hypothesis, so you can check it out and make sure you haven't made a mistake. And then the next line here is our test value. So they're telling me it's a z value, which is great because this was a z test, so it's trying to see through the glare, negative 0.23. So negative 0.23. Okay, so now what I like to do on my graph, I've shaded in my rejection regions. I like to take, especially if I have a different color, I like to take it and I like to make an X on the line where my test value is. So this is my test value. Okay? So then I know for sure I'm in that fail to reject region. Right in the middle. My value is not different enough from the null hypothesis to say that the null hypothesis is wrong. So when we fail to reject, we have to hedge our conclusion. So there is not enough evidence to, so we're not going to reject the null, so that means we cannot support our claim. To support the claim, the percent of female docs in Wenatchee is different than 32.4%. Okay, here's a last example for hypothesis testing proportions. So according to an online article published by The Hill, 55% of Americans said they wore face masks when they left the house to protect themselves from coronavirus. This was published on like May 13th, I think, online. After being at my local grocery store, I think this percentage is too high. At my grocer's, out of 30 people, 15 were wearing masks. Test my claim at alpha's 0.05. So, really, right, the hypothesis that we see is the alternative. I think this percent is too high. I think the actual percent of people who wear masks is less than 0.55. This is my claim. I think the percent is less than. So the null hypothesis, remember, has to have the equal sign. So P equals 0.55. So we'll gather the data. So I'm calling it info and some new notes. So I'll go ahead and write info up here. I think this percent is too high. At my grocer's, out of 30 people, so that was how many people I noticed. It's my sample size. And X, the number who had the characteristic of wearing a mask, so that's 15. So it's not asking for it, but I'll go ahead and do it. So P hat, this is, right, the proportion in my sample is 0.5. So here's our gather the data, is this info. So then our critical value, so alpha is 0.05. I have a one tail to the left. So alpha is 0.05, one tail to the left. So I have 5% here. There's your alpha on the left-hand side, 95% on the right. This is negative 1.96. I happen to remember that one. If you don't, you can either look it up or you can use that inverse normal and use your area as 0.05. So I've got that. I need my test value. So negative 1.96 for my critical value. Test value. I'm going to use my calculator again. So stat, test, it's option 5. So I can either arrow down or I can just type the number 5 and it starts with that. So change your P naught to be from your null hypothesis. X is 15, N is 30, and it's less than. I do have to change my alternative hypothesis to be the less than. And calculate. And there we go. There is our Z value, negative 0.55. They tell us P hat is 0.5. That P that's above it, your third line, don't worry about that yet. I will come around to it. This is called the P value. And we can use that as well to make our decisions. But for right now, we're going to use our test value, that negative 0.55. So our test value is negative 0.55. So I'm going to come over here to my graph. Right? Zero's in the middle. So negative 0.55. Is to the left of it, but not as far away as the rejection region. So the tails are the rejection region. The big meaty part is the do not reject region, fail to reject. So what's our decision? Well, our test value is in the meaty part, so we will fail to reject again. And we're failing to reject the null hypothesis. Remember, the decision is always about the null hypothesis. It's either fail to reject or reject H naught. Okay. So now let's go ahead and write our summary. So when we fail to reject, there is not enough evidence to support my claim the percent of face mask wearers is less than 55%. Now, I have potentially made a type 2 error, right? So I am not rejecting the null hypothesis that the percent is 55%, right? I'm not rejecting it, but it might really be false. So my value might actually be less, but I just happen to be there at a time when, right, more people were wearing masks than usually have happened. Okay, so this, right, I have a possible type 2 error, so I'm not sure. So that's why I'm saying I can't support my claim. I'm not saying that that it definitely is 55%. I'm just saying that I didn't gather enough evidence to say that it wasn't.